Okay, so we've talked about simple harmonic motion. We've introduced what it is. We've talked about restoring forces, and we've talked about how to describe simple harmonic motion, and we've talked about its connection to circular motion. Now we're going to go into talking specifically about springs and pendulums. But before you do, I want to ask a question. When I ask the question, then I want you to pause the video and then think about your answer before continuing. Here are four identical oscillators at different points in their motion. Which of these is moving fastest at the time shown? So go ahead and pause the video, think about that, and then restart to answer. Okay, so the correct answer here is going to be number A. The maximum speed of an oscillator occurs when that mass passes through its equilibrium position. This is the equilibrium position. Therefore, number A is the one that shows the oscillator at its maximum speed. Okay, so let's continue on talking about springs and pendulums. Okay, so here we see a bungee jumper as he lands in the water. As this bungee jumper falls, he increases in speed until the elastic cords attached to his ankles begin to stretch. That kinetic energy of his motion is transformed into the elastic potential energy of the cords. And once the cords reach their maximum stretch, his velocity will reverse and he rises back up. As he rises back up, that elastic potential energy will be transformed back into kinetic energy. If he keeps bouncing, this transformation happens again and again. This interplay between kinetic energy and potential energy is important to understanding simple harmonic motion. So here we see a vertical oscillator bouncing up and down, much like our bungee jumper here. If we were to throw energy into this, and say we begin with 2 joules of energy to begin with, when that oscillator reaches that equilibrium position, all of that potential energy it began with is converted to kinetic energy. As it passes through that equilibrium position, it will go transfer back into that potential energy, and then as it moves, we have areas where there's kinetic energy and potential energy, always equaling 2 joules due to energy conservation. Now, if we were to graph this, our graph would look something like this, where we've got our kinetic energy increasing and decreasing. We've got our potential energy increasing and decreasing, and our total energy remaining constant. Now, this graph would look the same regardless of whether it's a mass on a spring or a pendulum. The graph is going to look the same. The only thing that's going to be different is that in a spring system, that potential energy will be spring potential energy, and in a pendulum, that energy will be gravitational potential energy. So let's look at this in a little bit more detail. First, we'll look at a spring system, and then we'll look in more detail at a pendulum system. As we've talked about previously, the elastic potential energy of a spring that's stretched by some distance is 1/2 kx squared. Now, the potential energy is going to be 0 at the equilibrium position, and it's going to be a maximum when that spring is at its highest position, at its amplitude. Now, because there is no friction, we're going to ignore friction, and there are no other forces to do work on the system, then that mechanical energy is conserved. So what we've got is we've got energy switching between spring potential and kinetic. However, it always remains constant. So that at any point in time in this oscillator's motion, its kinetic energy plus its spring potential energy will be equal to its total energy. And as we can tell from the graph, the object has purely potential energy at its amplitude, at its high amplitude and at its low amplitude, and purely kinetic energy as it passes through that equilibrium point. So at its maximum amplitude, the potential energy is equal to 1/2 k times the amplitude squared. And at its equilibrium point, we have all kinetic energy at 1/2 mv squared. So since these two are equal to each other, the energy is conserved, we can set them equal to one another. to get 1/2 mv squared equals 1/2 ka squared. And if we were to solve this for the maximum speed, we can see that that maximum speed is related to the amplitude. And we see this relationship as the maximum velocity is equal to the square root of the spring constant over the mass times the amplitude. Now earlier we saw that in an oscillator the maximum velocity is equal to 2 pi frequency times the amplitude. Setting these two equal to one another and solving for the frequency, we're going to get 1 over 2 pi times the square root of the spring constant divided by the mass. Now remember, the frequency is the reciprocal of the period. So taking that in mind, a complete picture of the frequency and the period of an oscillating spring is given by these two equations here. This will give us the frequency and period of simple harmonic motion for a mass on a spring with a certain spring constant. What this tells us is that the frequency of a simple harmonic motion is determined by the physical properties of the oscillator, such as spring constant and mass. The frequency, and therefore the period, does not depend on the amplitude. So it doesn't matter how far we displace one of these spring oscillators, it's going to oscillate with the same frequency and same period with the same mass and same spring constant. So we're going to get a low frequency or a high frequency if we have a stiff spring with low mass. We'll get low frequency if we have a soft spring with high mass. So let's switch over now and talk about pendulums. If we were to do a similar derivation as we did for a mass on a spring for a pendulum, we would find that the frequency and the period are related by these equations here. Here's a frequency, 1 over 2 pi times the square root of g, 9.8, over the length of the pendulum. The period is given by 2 pi times the square root of the length of the pendulum over g. Now what does this tell you? This tells us that the frequency and therefore the period of a pendulum does not depend on the amplitude or the mass of the pendulum bob, which is a real big misconception for a lot of people. A lot of people will think that the mass of that pendulum bob will determine how quickly that thing swings. But it doesn't. The period and frequency depend only on the length of the pendulum, and g, of course, is a constant. So say, for example, we wanted to design a clock so that with one swing of the pendulum in either direction takes 1 second. If we want to figure out how long we have to make our pendulum. Well, we're going to start by using the equation then for the period of a pendulum. Now, if one swing, so one back, takes 1 second, that means the full period of this, which the period is the time for a complete oscillation, is going to be 2 seconds. So we substitute in our values, we divide by 2 pi, we get 0.318 equal to the square root of L over 9.8. Square both sides, solve for the length, we end up with 0.993 meters. So 99.3 centimeters will be the length of that pendulum, regardless of the mass at the bottom. So that's mass on a spring and pendulum simple harmonic motion. And we can transfer that into real physical situations, such as your shock absorbers in your car. You've got 4 tires, you've got 4 essentially springs that oscillate up and down every time you go over a bump. Your leg as you walk acts as kind of like a pendulum. So we can see these systems acting in the real world. Your textbook goes into a little bit of discussion about what's called damping. Damping is, we don't really have to go into detail over it, but just have an understanding that damping is simple harmonic motion where obviously you got a spring that's oscillating, it eventually slows to a stop. You've got a pendulum that swings, it eventually slows to a stop. It does that because of drag forces with the environment. It will decrease then in amplitude over time. That's called damping. And really the main points in damping is that initially there's a large difference in the amplitude, but as time goes on, that difference gets much less, and then ultimately that damping is due to drag, and there's something called the time constant that determines how quickly that amplitude will decay. Like I said, though, we don't need to go into the details of that. The last thing that we do need to talk about is this concept called resonance. Now, if you shake a cup of water, the water will slosh back and forth. This is an example of an oscillation that's subjected to a periodic external force, which is called a driven oscillation. You can also think of a driven oscillation as like if you push somebody on a swing, right? You're constantly putting energy into that oscillation, so it's called a driven oscillation. Other driven oscillations are like the electromagnetic coil in the back of a speaker will provide a periodic magnetic force to drive that cone back and forth, causing it to send out sound waves. Earthquakes are another example of a driven oscillation. All that means is that it's just an oscillation that is driven by some external force. Now, if we imagine an oscillator that, when it's left to itself, oscillates at some frequency, we call that frequency its natural frequency. Okay, so all things actually have a natural frequency at which they will oscillate. If we then subject that system to some periodic external force of some other frequency, that frequency is called the driving frequency. Now, the driving frequency is completely independent of the oscillator's natural frequency. Somebody or something in the environment selects the frequency of the external force, causing the force to push on the system so many times per second. For example, with our cup of water, right? If you just nudge the cup of water, you'll notice that the water will slosh back and forth at a particular frequency. That's its natural frequency. Now you shake the cup at some frequency, that's the driving frequency. As you shake the cup, the oscillation amplitude of the water depends very sensitively on the frequency of your hand. So if the driving frequency is near the natural frequency of the system, the oscillation amplitude may become so large that water splashes out of the cup. So any driven oscillator will show some similar dependence of amplitude on that driving frequency. Suppose a mass on a spring has a natural frequency of, say, 2 hertz. You can use an external force to push and pull on the mass at some other frequency, measure the amplitude of the resulting oscillation, then repeat that over and over for many different driving frequencies. A graph, if we were to graph the amplitude then versus the driving frequency, we get what's called a response curve. If we look at the left and right edges of this response curve, we see that the driving frequency is substantially different from the oscillator's natural frequency. The system oscillates, but its amplitude is really small. The system simply doesn't respond well to a driving frequency that differs much from its natural frequency. As the driving frequency gets closer and closer to the natural frequency, the amplitude of the oscillation will rise dramatically. We could say that the natural frequency is the frequency at which the system wants to oscillate as much as the system can want something. So it's quite happy to respond to a driving frequency that's near that natural frequency. So the amplitude reaches a maximum when that driving frequency matches the system's natural frequency. This large amplitude response to a driving force whose frequency matches the natural frequency of the system is called resonance. And within the context of driven oscillations, that natural frequency then is often called the resonance frequency. So if you get some system oscillating at its natural frequency, and then you provide a driving frequency that matches that natural frequency, you're going to get resonance and a high amplitude. A classic example of this is the use of sound to break a glass. If you've ever tapped like the edge of a wine glass, you know that it has a certain natural frequency at which it will vibrate. So if a sound wave of just the right frequency vibrates the glass, it's possible to increase the amplitude of that oscillation so that to such a degree that that glass will actually shatter. And resonance is quite important when we start talking about sound later on. We'll look at a couple of examples and demonstrations of resonance in class. So we're going to end our discussion here of simple harmonic motion with oscillating springs and pendulums, and we'll see you in class.